In this video, I'm going to demonstrate how to graph a tangent or a cotangent function in the Connect Math and ALEKS graphing systems. So this problem is a tangent problem, but keep in mind you would follow essentially the same steps to graph a cotangent. So as with any problem, let's make sure we read the directions really carefully and then work as much as we can on paper, not only to get the practice, but also so we make sure that if we make a mistake, we have something where we can go back and we can find our mistakes. So let's go through the directions first. So for this tangent function, y is equal to the tangent of 2x minus pi over 4. We want to plot two consecutive asymptotes, and then between the asymptotes we want to plot a point corresponding to an x-intercept, and then two additional points, one on each side of that first point. So keep in mind when we actually graph the function, what we're thinking of as an x-intercept may not actually be a point that crosses the x-axis, but think of it as the point that would normally cross the x-axis on the standard tangent periods graph, and then potentially has been moved based on whatever has happened in this function. So what we normally graph are a pair of asymptotes and then the 3 points between those. So those points that we normally graph between those two asymptotes, that's exactly what the system is looking for. So once we have our graph on paper, all we need to do is translate it to the system and we'll have exactly what we need. So let's flip back over to the paper and let's get started. Now, this problem did not ask for us to directly identify the function attributes, but I like to start there because those are going to be the things that are reflected on the graph anyway. So we'll start by identifying the amplitude, the period, the phase shift, and the vertical shift of this function, those that apply. So first for amplitude, remember amplitude means height. It tells us how far up and how far down the graph goes to hit its relative maximum and minimum. With a function like tangent that increases and decreases without bound, we don't actually have an amplitude, so we'll just list it as none. Keep in mind the number that we would normally associate with amplitude would be 1. If we had something other than a 1 in front of the tangent, we could just think of that as being reflected on the graph as a vertical stretch in a sense. So whereas we normally go up to 1 and down to 1 to plot to -1, to plot our key points, we would change those values accordingly based on whatever number was in front of the tangent. But to be official, no, we don't actually have an amplitude for this function. Okay, now let's go to our period. Remember, this one's kind of special. So our four original functions, sine, cosine, cosecant, secant, they all have periods of 2 pi. Tangent and cotangent are different. The original period for tangent and for cotangent is actually pi. The values for those two functions, as well as the graphs, actually repeat over a shorter distance rather than the 2 pi that we see for the other 4 functions that we normally graph. So standard period for tangent is pi. And we know we need to divide our standard period by whatever the coefficient for x is. So we're going to divide it by 2. So normal period for tangent is pi. This period for this function is going to be pi over 2. So essentially we complete one period of the function in half the normal amount of time, half the normal distance. Okay, now let's look for a phase shift. Anytime we have addition or subtraction inside of our trig function, we have a phase shift. So we're subtracting pi over 4. Now remember, the signs are a little bit weird here. Whenever we subtract inside of the function, the phase shift is actually positive. We're moving in the positive direction. So if this is negative, it's a positive phase shift. If this is positive, it's a negative phase shift. So because this is negative, it's going to be a positive phase shift. And then we also need to divide this value by that 2 as well. So don't make the mistake of thinking the 4 and 2 cancel. Remember, this is fractional division, and so to execute this, we multiply by the reciprocal of the denominator, which is going to give us pi over 8. So we'll have a phase shift of pi over 8 units to the right of where our normal period starts. Now vertical shift, if we have an addition or subtraction outside the function, that corresponds to a vertical shift. We don't have any of that, so there is no vertical shift in this case. Okay, so we know all the key attributes of this function. Now let's determine how our labeling is going to work. So this is also a point where things change, and they're just a little bit different for tangent and for cotangent. A couple things actually change for tangent. So of course the period changed. Both tangent and cotangent have a period of pi, but tangent is actually the only function where we don't normally start graphing from 0. We actually start graphing from not 0 but negative pi over 2. Our standard period for tangent goes from negative pi over 2 2 pi over 2. And the reason we graph over that interval is because that's going to be natural locations where the asymptotes for the tangent function are going to fall. So rather than starting at 0 like we normally do, if we think of negative pi over 2 as the starting point for our period, then we automatically generate one asymptote followed by 3 points, followed by another asymptote, and we get a better sense of what the tangent function actually looks like over one period. So our standard left-hand endpoint for tangent is going to be negative pi over 2. Right-hand endpoint will be positive pi over 2. And we want to see how these endpoints are affected by the fact that we have that 2 and that negative pi over 4 inside of our function. So I'm going to write my inequality with my standard endpoints, and then I want to isolate my x to see how these two values are going to impact these endpoints. So I'm going to start by adding my pi over 4, moving it over. So keep in mind, negative pi over 2 is the same thing as negative 2 pi over 4. So if we add pi over 4 to negative 2 pi over 4, we'll have negative pi over 4. Okay, and then pi over 2 is the same thing as 2 pi over 4. So if we add pi over 4 to 2 pi over 4, we'll get 3 pi over 4. Okay, and then we also need to divide by 2. Divide both of those endpoints by 2 as well. Keep in mind 4 and 2 don't cancel. The 2 is actually multiplied by 4, exactly as it happened here. So negative pi over 4 divided by 2 is going to be negative pi over 8. And then our x is isolated, which was the goal. And then 3 pi over 4 divided by 2 is going to be 3 pi over 8. So whereas the normal tangent graph starts at negative pi over 2 and pi over 2, those are going to be the locations of vertical asymptotes. Our normal vertical asymptotes fall at those locations. The vertical asymptotes for our function are going to fall at negative pi over 8 and 3 pi over 8. And then we'll have our standard 4 intervals between those two values in order to get those key points for this particular graph. So the next thing we need to know is, okay, we start at negative pi over 8, we end at 3 pi over 8. Where are we falling in the middle to hit those key values? How are we traveling from our starting point to our ending point? In other words, if we take our whole period and divide it into 4 parts, how are those parts sized? So to determine how to label a little bit further, I'm going to take my period, I'm going to divide it into 4 equally sized parts, which is going to give me pi over 8. So that tells me I'm counting by pi over 8 as I label my horizontal axis in order to determine where all of those key locations fall. Okay, so let's start labeling. Let's start vertically. Now we didn't have an amplitude change, we didn't have a vertical shift. Because there's no vertical shift, the center is still at 0. And because there was no amplitude change, ultimately there's no amplitude at all, but there was no stretch. There was no number in place of amplitude, the number we normally associate with amplitude, that is. We know we go up to 1, we go down to negative 1. So nothing special is happening vertically speaking. Now let's look at the horizontal axis. We know we're starting at negative pi over 8. So I'll start labeling at negative pi over 8. And then we travel 1, 2, 3, 4 units, 4 intervals, divide our period into 4 intervals. And the period is going to end at 3 pi over 8. Okay. So if we divide this period into 4 equally sized parts, where do those individual values fall? Well, we know everything is pi over 8 units from the previous thing. So starting at negative pi over 8, if we add on pi over 8, we get to 0. Starting from 0, add on pi over 8, we get to pi over 8. Pi over 8 plus pi over 8 is going to be 2 pi over 8, which reduces to pi over 4. And then pi over 4, or 2 pi over 8, plus pi over 8 takes us to 3 pi over 8. So that's exactly what we expect to have happen. Okay, so again, the benefit of graphing this way is these values represent vertical asymptotes. So where we start and where we end, those are going to be the locations for our vertical asymptotes. So let's start by putting those on the graph. Now when I have an asymptote that actually falls on one of my axes, I like to draw it just to the left or to the right of it so you can actually see it. And then we'll put our other asymptote over here. Okay, and then we just fill in our points based on the standard shape for our tangent graph. So remember, tangent increases from left to right. halfway between our asymptotes is where we hit our x-intercept. So in this case, this truly is an x-intercept because this is the actual x-axis. This would be the location of the y-axis, so it's worth noting. That's where our actual y-axis would be. So this vertical axis we're using to label, to graph, is not actually the y-axis. Here's 0, so this would be where x equals 0 falls, aka the y-axis. So this is an x-intercept. Okay, we know we have a point down at -1 to the left of that, and +1 to the right of that, because again, tangent increases from left to right. So we follow our asymptotes, cross through those 2 points, and that's going to be the period for our tangent function. So we have 2 asymptotes, we have an x-intercept between them, and then we have 1 point on either side of that x-intercept. So we have exactly what our system is looking for. Okay, let's flip back over and let's see if we can input that into our graphing system. Okay, let's look at the grid. So notice the grid is labeled based on, horizontally speaking, units of pi/8. So our scale is pi/8. So because we fall at multiples of pi/8 as we traveled along the period, that means we should be able to just drag and drop our points. We also had y values at -1, 0, and 1. And we're labeling the y-axis here just using integer values, so again, that's a good thing. That means we can use the pencil for everything here. Now let's start with our asymptotes though. So our first asymptote, our leftmost asymptote, was at -pi/8, so we'll place that. And then our right asymptote was at 3pi/8. Now we can plot our points. So our x-intercept was at pi/8, halfway between the 2 asymptotes. We had a point at 0, -1. We also had a point at pi/4 and +1. Now it's worth noting we were able to do everything with a pencil here. What if you weren't able to do that? What if the grid wasn't labeled in such a way that you could actually just drag and drop points? Well, that's when you use the plot a point tool. So if something falls between grid lines and you're not able to use the grid lines to just drag and drop a point with the pencil, that's where you would actually use the point plotter, and you'll just type in the values you need and it'll plot the point accurately for you. Make sure you don't do any rounding. As I've mentioned before, rounding does not work in this system. You have to use exact values because it's essentially taking all the features that you've generated on the graph and it's determining what function matches those values and what the graph of that function would be. So if you use approximations, it's not going to match to the correct function and the correct graph, and you're not going to get an accurate graph when you connect the points. So if you need to use the point plotter tool because the grid's not working for you, feel free to do that. So once we have our 3 points, we have our 2 asymptotes, everything the system wanted, we can do the graph of function. Notice it graphs more than just that one period that we actually plotted. It graphs the whole function with the understanding that everything continues in the same way to the left and the same way to the right. So let's check our answer. And it looks good. So what does it mean if your graph didn't turn out correct, if maybe the shape wasn't matched with what a tangent's graph shape should be? Maybe you didn't generate enough information. You need 2 asymptotes, 3 points between them, 1 point corresponding to an x-intercept. All of those features have to be there for it to graph accurately. So if you're missing one of those features, it may not graph it correctly. If otherwise you have all those features, more than likely it means one of your points was wrong, or maybe you placed an asymptote incorrectly. So go back to your paper, double check everything you did on paper, make sure you didn't make a mistake, for instance with that, setting up that inequality to determine the endpoints, to determine where the vertical asymptotes fall. Remember, tangent's kind of special. Normally starts at -pi/2, goes to pi/2. If you accidentally start at 0, then you're not going to get the correct locations for your asymptotes. So that's one possible mistake you can make. Ultimately, just go back and check your work, make sure you didn't make any arithmetic mistakes, and that should help you fix your graph. So that's graphing tangent and cotangent functions in Connect and ALEKS.